Okay, hey, I hope everybody's doing well. Today we're going to start with 4.2 on page 101 in your textbook. We're going to be talking about acceleration. So most of you guys probably have either bought a car or you're getting ready to buy a car, things like that. And when we're looking at cars, we always want to know how fast the car will go. And 0 to 60, right? That's the big thing that all the car people talk about. And what that is called is acceleration. And acceleration is the change in velocity per unit time. So in other words, it measures how quickly velocity changes. So up here you can see that I've wrote average acceleration equals change in velocity divided by elapsed time. Now what that really means is final velocity minus the initial velocity divided by time. So 60 minus 0 divided by time, say 30 seconds. So this final velocity minus initial velocity is your change in velocity. And this delta sign here, the triangle delta V, just means change. A for acceleration and T for time. And what this formula actually looks like is A, which is your acceleration, divided by your change in velocity, equals your change in velocity over time. Or, to even calculate this further, velocity final minus velocity initial over time. This is going to be a very important formula that we'll use. Another way to look at that would be delta V equals acceleration times time. That's your change in velocity equals acceleration times time. Okay, so again, this delta here, this triangle means change in. So let's look at an example. If we had a dragster that starts from velocity, from rest, so rest, it's not doing anything, would be 0 feet per second. So our velocity equals 0 feet per second. This is at rest. And attains a speed of 150 feet per second and 10 seconds. Okay? And what that means is the change in velocity would equal 150 feet per second, because that's your final velocity, minus our initial velocity, which is 0 feet per second. It's going to give us 150 feet per second. Again, our time equals 10 seconds. So what it's asking for is our acceleration. What does that equal? Well, we know that delta V equals A times T. That's the formula we start with. So we're looking for acceleration here. So if we multiply both sides by T, we would get A equals delta V over T, because we have delta V here and we have T here. So then we can solve for our equation. So 150 feet per second divided by 10 seconds, and that's going to give us 15 feet per second per second. 15 feet per second per second. Now, let's look at that for a minute. You got to remember that to simplify a fraction in this form, so if it's AB over CD, we have to divide. So that's going to be AB divided by CD. Now remember, when you're dividing fractions, the other side you invert it and multiply. So that's going to be AB times DC, D over C. So that's going to equal AD, multiply AD times BC. Okay? So when you do all that, then it's going to look like this. 15 feet per second divided by a second over 1, because that doesn't change anything, right, when you put it over 1. So that way you can solve it. So this is going to be 15 feet, hope I don't run out of room, divided by seconds, divided by seconds over 1, which remember we're going to multiply and switch it. So let's see what that's going to be. Times 1 over seconds. So that way you can get rid of everything. Remember, that's going to be feet times second squared. So it's going to be 15 feet per second squared, because seconds times seconds is squared. Okay? So you can pause it here and look at that and make sure you understand it, but that's very important in these problems. And also, there was a question that came up today about your problems in the back of the book. Your answers sometimes don't come out exactly. Well, that's because in the back of the book they're using they're not rounding, okay? They're using certain significant digits, so 1 to 3 or whatever significant digits. So if you don't get it exactly right in your rounding, that's why, okay? And that's fine unless it's asking for a certain significant digits. If it tells you that it wants it in 2 decimal places or whatever, then I expect you to do it. But if it's not asking for that and you're not rounding too much, then that's perfectly fine. I can figure that out, okay? All right, so let's look at another thing. If a plane accelerates at 8.5 meters per second squared for 4.5 seconds, find the increase in its speed in meters per second, okay? So let's look at that. So our acceleration, it says, is 8.5 meters per second squared. And it said our time is 4.5 seconds. So it wants to know what our change in velocity is. Now remember, our formula for change in velocity equals a times t. And also, the way I suggest you work these problems, and any problem you do in physics or any of our other classes, mine or Andy's, is write down all the information you're given, write down what you need, and that way when you look at your formula, you can see which one to best use. And you're going to see in a minute you have a lot to choose from. So make sure that you do that, and it'll kind of help you decide on which formula that you're going to use, okay? So now if we multiply this out, acceleration was 8.5 meters per second squared times our time, which is 4.5 seconds. When we multiply that, now because this is meters over second squared times seconds, actually seconds, hold on, seconds are going to be up here, seconds, we can get rid of this, okay? And that way you have seconds left because you want it to be in the same units. So when you multiply this out, you're going to get 38 meters per second. So if you're still having trouble on how to cancel and all that, please look back at your notes, okay? Now that's how we calculate change in velocity. Now we've been talking about acceleration, but there's actually something else that is important, right? So what happens when you put on your brake in your car? You de-accelerate, right? You don't necessarily go backwards until you put the car in reverse. But if you're going at a certain speed and you put on your brake, you're going to de-accelerate, okay? And that's very important too. And when you do that, you use a negative number for that, okay? So, for example, if a car is accelerating on a straight road, both the direction of the velocity and the direction of acceleration are along the road in the direction which the car is moving. When the car begins to slow down, the direction of the velocity is understood to be along the road in the direction pointing ahead of the car. And the direction of acceleration or deceleration, it is understood to be along the road in the direction pointing behind the car. Okay? So a driver steps off the gas pedal and consists of a rate of minus 3.00 meters per second squared, and time is going to be 5 seconds. Now notice here they use 2 decimal places for these values. So in the back of the book it'll show you 2 decimal places for the answer. Sometimes 1. They'll drop off one of the zeros if it's all zeros, okay? Now it said that it originally traveling velocity of 20 meters per second. So that's initial, right? It begins with that. So it's going to be 20 meters per second. Okay. Also notice that this one only has 1 significant digit, and so the answer is going to be the smallest amount of significant digits. So the answer will be in 1 significant digit. Okay. Just kind of showing you some things as we go. And what we're looking for here is our final velocity. So we don't know what that is. So we know that our formula that we've been using is change in velocity equals a times time. Now we also know that this change in velocity is VF minus VI equals a times time. Okay? And we're looking for VF, so we got to solve for VF. So we're going to subtract both sides, or add both sides of VI. Okay? So that cancels, and we get VF equals AT plus VI. And we have AT and we have VI. So we plug everything in. Our A, let's see. Well, they started with VI. We'll just do that. So VI, or we can do it this way. So minus, no, we better not. Oops, sorry about that. Let me erase this. So VI is 20 meters per second plus our acceleration. Now remember, it's minus 3, okay? So it's very important. Minus 3 meters per second squared times our 5 seconds. Okay? So we multiply all this out, we get 5 meters per second for our final velocity. Okay? So when you work these out, that's the only formula you'll need to know. Now you may have to manipulate it, so you may need to know T, or you may need to be, you may need to find T, you may need to find A, you may need to find VI, you may need to find VF, or you may need to find the change in V. Okay? So that's how you work those to find those values. I want you to do problems 1 through 23, the odd, on page 104. Okay? And I'll put in when those are due. Now we also need to take a test. I'm trying to decide if I just want to add chapter 2 to the next test, or if I'll just give you a short quiz for a test on chapter 2 and just make it a few problems. But I'll decide that right after I record this lecture. Alright, so this was 4.2. 4.2 on page 104 is the problems, okay? Alright, so the next thing we're going to talk about, and the last thing on this lecture, is going to be 4.3, and it's on page 105. And we're going to build on to that equation that we've been working on. This time we're going to talk about uniformly accelerated motion in free fall. And I need you to study on page 105. There's a set of formulas, and I don't want to write all these down because you can look at it. But page 105, you need to look at 1 through 6 formulas and what they are, okay? And depending on what your problem's asking for, you may have to use one of these equations, so you're going to have to pay close attention, okay? But uniformly accelerated motion of an object occurs when its acceleration is constant. So examples are a ball rolling down a straight incline, a car increasing in its speed at a constant rate, and a ball dropping from a building. And you can find any of this using these equations and applying your problem solving methods. Now the best thing to do again is write down everything you need, okay, and then figure out which equation you need to use. So let's look at an example. This is example 1 on page 106, I'm sorry. So the average velocity of a rolling freight car is 2 meters per second. So the average velocity is 2 meters per second. Okay, and then it says, how long does it take for the car to roll 15 meters? So our displacement is 15 meters. It wants to know how long it takes. Okay, so we're looking for T. Now, if you look back over at your formula sheet, formulas on page 105, and I'll give you these formulas for the test, okay, so you don't have to worry about that. If you look at that, then we need to find, we know we're looking for time, we know we have average and displacement, so you look over here for average and displacement and what you can use, okay? So let's look at the formula. So S equals V average times time. That's our basic formula, okay? So we need to solve for time. So you're going to multiply both sides by V average. So let's just write this out. V average times time. So multiply both sides by V average. That's going to cancel. So T is going to equal S over V average. Okay, so we got our basic equation, we solved for time, and now we can solve it. So S is going to be 15 meters, that's our displacement, divided by our V average, which is 2 meters per second. So time then, meters are going to cancel, is going to be 7.5 seconds. Okay, and that's how you solve it. All right, very good. Let's look at another one. A dragster starting from rest reaches a final velocity of 318 kilometers per hour. Find its average velocity. All right, so it says a dragster starting from rest. Anytime it starts from rest, VI is going to equal 0. Okay? If it says from rest, it's going to equal 0. Okay? Our V final, it says, is going to be our final velocity of 318 kilometers per hour. Find its average velocity. So we want to know V average. So if we look at our formula sheet over there, we have acceleration equals VF minus VI over T. We also have V average equals VF plus VI over 2. I believe that's the one we're going to use, okay? Because we have VI, we have VF, and we're looking for V average. So we're going to use the first formula on page 105. So that's going to be V average equals VF plus VI over 2. So our V final was 318 kilometers per hour plus 0 kilometers per hour. They need to be in the same units too, so verify that. Divided by 2. Always make sure your units are in the same your units are in the same format. If not, you need to convert them to that format. So now this is going to equal 159 kilometers per hour. Okay, the average. All right, let's try another one. The next one, it says a train slowing to a stop has an average acceleration of -3 meters per second. So our acceleration is -3 meters per second squared. Now, if it's a negative there, we know that it's slowing down, don't we? It's a deceleration. It's deceleration, okay? So remember that. If you ever see a negative, you know that it's slowing down. Alright, then it says, note that a minus acceleration is commonly called deceleration, meaning that the train is slowing down. If its initial velocity is 30 meters per second, so initial velocity is VI, 30 meters per second. How far does it travel in 4 seconds? So it also gives us time. Okay, and then we're wanting to know how far, so we know that's displacement. Okay, so write down everything that you know and then figure out what your formula is going to be. Now for this one, our formula, we know we're looking for displacement, so there's a formula for displacement that's S equals V initial, which we have, times time, equals 1/2 acceleration, which we have, times time squared. Perfect. We have everything we need. We don't have to manipulate it because this is plus here, sorry, because it's giving us what we need and we're solving for S, okay? Alright, so we can just plug everything in, pretty simple. So we've got V initial is 30 meters per second times time, which is 4 seconds, plus our 1/2 times our acceleration. Now don't forget that negative sign, is 3 meters per second squared times time. Now time is squared, so 4.0, whoops, what in the world? 4.00 seconds squared. Okay, now when you square that, you got to square seconds also. So then when you multiply that, you get 120 meters minus 24 meters, and that's going to equal 96 meters for our displacement. So it's going to go 96 meters. Okay. Now let's look at one more. On this one, we've got an automobile accelerates, okay, to 67 kilometers per hour to 96 kilometers per hour in 7.8 seconds. What is its acceleration in meters per second squared? So we know our final distance, or final velocity, is 96.0 kilometers per hour. We know our initial C, it didn't say from rest, it gives us 67, so our V initial this time is going to equal 67 kilometers per hour. Our time it's going to take is 7.80 seconds, and this time we're looking for our acceleration. Now it tells us what acceleration needs to be in meters, so it needs to be in meters per second squared, and we're in kilometers per second squared, so we'll have to look at that. Kilometers actually. Alright, so the working equation is going to be the same as we did earlier, I believe. So we have initial, we're looking for acceleration, we have V final minus V initial over T. So we have everything we need. We have V final, V initial, and T, and A. So that's going to be number 2 in our equations on page 105. So when we go ahead and plug everything in, velocity final is 96 kilometers per hour minus velocity initial 67 kilometers per hour divided by our time, which is 7.80 seconds. Okay, so let's go ahead and solve this part. 29 kilometers per hour divided by 7.80 seconds. Okay, now we need to convert kilometers from meters to kilometers, okay, or kilometers to meters, because it said it needs to be in meters second squared. So that's going to be 29 kilometers per hour. And we can make this where you can see it better if you need to. So the 29 kilometers per hour, it might be easier to cancel, times, now how many kilometers in a meter is 1,000, so that's going to be 1,000 meters divided by 1 kilometer, and that'll cancel those two, times, and it says it needs to be in seconds squared, and we're in seconds. So that's going to be 1 hour divided by 3,600 seconds. Okay? So kilometers cancel and hours cancel. So now that'll give us meters per second. And all of that is going to be divided by 7.80 seconds. So we do that, we end up with 1.03 meters per second squared for our acceleration. Okay? So if you need to stop it here and work that problem and make sure that you can do that, that'll be great. But this gives us our meters second, and then this is second, so it's going to be squared. Alright. Let's do one more that's important, I think. So if you have a rock and it's thrown straight down from a cliff with an initial velocity of 10 feet per second. So VI equals 10 feet per second. Its final velocity when it strikes the water below is 310 feet per second. So our V final is going to be 310 feet per second. The acceleration due to gravity is 32 feet per second squared. Acceleration due to gravity is 32.2 feet per second squared. Okay. How long is the rock in flight? So they want to know T. Alright, so a ball falls with constant acceleration. A equals G. So another way to look at gravity is A equals G equals 9.80 meters per second squared. So depending on if you're using which type of units you're using, but that's another way, 32.2 feet per second or 9.8 meters per second squared. With the speed and the distance traveled calculated at given times. Because the ball was dropped, V initial equals 0, right? And the formulas for a VF and S are shown simplified. Note how the velocity and distance traveled increase during each successive time interval. So look at page 109, and at T0, you start at 0 meters per second. At T1, you can see how it speeds up, okay? So if you look at your formula, your basic equation, there's two of them you could look at. Okay, one of them is VF, if you're looking for final velocity. VI plus AT. Or another one is A equals VF minus VI over T, if you're looking for acceleration. But now we're looking for time, so we want to say if we solve this one for time, you're going to get VF minus VI over A. Okay, so we're just rearranging that formula for time. So time equals 310 for VF, feet per second, minus VI, which is 10 feet per second, divided by, and it's feet per second, so we're going to use 32.2 feet per second squared. Okay? Did I write that down wrong? Yeah, this should be, oh, that's right. Okay? So then, when we solve this, we get 300 feet per second divided by 32.2 feet per second squared. And that's going to equal 9.32 seconds. Okay. Now how would we solve this feet per second and feet per second squared to get this to be seconds is like this. So if you get feet per second divided by feet per second squared, and let's just rewrite this, feet per second divided by feet per second squared. Now remember, you got to flip it and multiply it. So feet per second times second squared over feet. So that's going to cancel that. And then that's going to cancel and you have an S left. Okay? And that's where that comes from. Alright, so I want you to read through this chapter. Make sure you read these chapters and work through these problems. They really are helpful. Okay? And it makes you understand things a little better. Also look at the terminal velocity of an object on page 112 and look at those formulas on page 105. Okay? Now I want you to work problems 1 through 31 odd on pages 112 through 114. And both of these homeworks will be due at the end of the week. You're also going to have a short quiz that'll be due Monday afternoon. Okay, I'll give you all week to work it. It'll just be a little short quiz on chapter 2, I believe, but I'll get back with you on that. Okay. Let me know if you have any questions, and I'll be glad to help you. And good luck. Thank you. Y'all have a good day. Okay.